Hello, everyone, and welcome back to the Jamaican Geologist YouTube channel. So, this is episode 4 in our Geology Foundation series. And in this series, of course, we explore the basics and present complex concepts in a fun and engaging way. If you remember the last episode, we looked at the structure of the atom, atomic bonding, and isotopes. Today, we are stepping up as we are leaving the atomic world and observing substances we can often see with the naked eye. We are entering the world of minerals, and in this episode, we will learn what minerals are and how to identify them. I expect this to be fun as I will have some demonstrations as well. So I'm excited and I hope you are too. So let's begin. So, what is a mineral? I mean, we hear the word tossed around all the time. We hear things like, this food is packed with vitamins and minerals, and things like mineral water and mineral oil are marketed to us by corporate entities for the health of our skin and body. In Jamaica, we hear of and we oftentimes visit mineral baths and spas. There is the Rockfort Mineral Bath, there's Milk River Mineral Bath in Clarendon, and then there's Bath in St. Thomas. So, what is my point? What I'm trying to say is that minerals mean different things to different people. A doctor and a dietitian will have a different conceptualization of minerals than, say, a massage therapist. And in geoscience, we too have our own ideas. I mentioned this in another video on this channel called Minerals the Basics, so you can check that out. But for the purpose of this video and channel, I will deconstruct the definition of what a mineral is to a geoscientist, and we will create a checklist for labeling a substance as a mineral or not. So the Oxford Dictionary of Geology and Earth Sciences defines minerals as usually inorganic substance which occurs naturally and typically has a crystalline structure whose characteristics of hardness, luster, color, cleavage, fracture, and relative density can be used to identify it. Each mineral has a characteristic chemical composition. Rocks are composed of minerals. More loosely, certain organic substances obtained by mining are termed minerals. Okay, that was quite a mouthful, so let's look at another definition. Now, Dexter Perkins in his book, Mineralogy, noted that James D. Dana came up with the first widely used definition, which forms the basis of the definition we use today. Dana defined a mineral as a naturally occurring solid chemical substance formed through biogeochemical processes having characteristic chemical composition, highly ordered atomic structure, and specific physical properties. Okay, so there is there are a few themes or key words coming from those definitions. We see, for example, naturally occurring. We also see chemical composition. We see ordered atomic structure. And we also see crystalline structure. And these terms or keywords are what form the basis of the mineral checklist. Now, because of my geology background, especially when I worked in the capacity of geologist with the government of Jamaica, people used to come with all kinds of things all the time and ask me, what is this? And now if someone comes to you and asks you if this is a mineral and what kind of mineral or rock it is, there are some fundamental things you need to ask yourself. And this is where the checklist derived from the definitions earlier is an excellent place to start. The first thing to ask yourself is it natural? This is usually very obvious. So when a farmer from Trelawney, for example, says, I found this thing on my farm, youngster, and do you know what this is? That usually ticks off the first thing on the list. But there is some debate about this, as we can now synthesize minerals in labs. For example, there are lab-grown gems like lab-grown diamonds, and this, some purists often say, doesn't fit the traditional definition. But my personal take is that these things we synthesize in labs, they have the same atomic arrangement, and they can and do occur in nature too. So technically they're still minerals in my opinion. But the next question is it inorganic? Minerals are inorganic, which means they are not built from carbon-based organic compounds that make up plants and animal tissue cells. There is a caveat though, as many animals build mineral skeletons and mineral shells. The next question is it solid? Minerals are solid, not liquid or gas at Earth's surface temperature. The next thing is, does it have a defined chemical composition? Each mineral has a defined chemical composition, which is a combination of elements, and these elements bond to form a particular crystal structure. Remember, we discussed elements and how they bond in our previous episode, so you can check that out too. Does it have an orderly atomic structure? When atoms combine to form minerals, they do so in a way that creates a geometric signature or pattern called a crystal lattice. But we will get into all of that soon. If the substance in front of you ticks all of these boxes, then it is likely a mineral. But in my experience, people who are not geoscientists usually don't care if it's a mineral or not. Most people don't care about atomic structure or if it's a perfectly formed crystal. What most people want to know when they approach me is, what is it and does it have any value? I will explain some other diagnostic properties in a moment. Okay, so before I get into the common diagnostic features, I want to note color. Now, people often say things to me like, this mineral is red like my birthstone and it looks like it, so it must be it. Or mineral X is a nice yellow color like mineral Y, so they must be the same. Color is the result of light being absorbed or reflected off an object, and although in some cases it helps us determine what the mineral is, in the majority of cases color can be very unreliable. For example, sometimes very tiny amounts of other elements called impurities get into the mineral structure without changing its composition, and this creates a variety of different colors of the same mineral. A major diagnostic feature we can use to pinpoint or pin down what a mineral is hardness. Hardness is how well a mineral resists being scratched. Scratching the surface of a mineral deteriorates the structural integrity by breaking the bonds between the atoms. So you can think of hardness as a kind of mineral strength, if you will. We often test mineral hardness through a scratch test or a series of scratch tests with a guiding chart called the Mohs scale of mineral hardness. It was developed by a German mineralogist named Friedrich Mohs. the scale ranks minerals from 1 to 10 based on their ability to be scratched with common items. So it's more of a relative scale than an absolute one. So talc is the softest mineral and it is at a 1 on the scale, while diamond is the hardest at a 10. Your fingernails have a hardness of 2.5, a copper coin has a hardness of 3.5, and a knife or a glass plate has a hardness of 5.5, and so on. And I will demonstrate how we use the scale in our next segment. Okay, so here we have a set which represents the Mohs scale of hardness. I have a steel nail, I have a glass plate, and I also have a copper coin. And of course, we all have fingers and fingernails. So talc is the softest mineral. So it's talc, then gypsum, calcite, fluorite, apatite, orthoclase, quartz, topaz, corundum, and diamond. But for these sets that they manufacture, or they put together rather, they instead of diamond, because diamond is quite expensive, therefore the sets will probably get really expensive, they substitute it with silicon carbide. And silicon carbide is traded in the jewelry business as moissanite. I mean, when it's cut and polished, it's really beautiful. It has a nice fire and brilliance, and a lot of people use it in their wedding sets these days. It's a good substitute for diamond. Whereas diamond is a 10, silicon carbide is like a 9.25 to about a 9.5. So it's a very good substitute, so it's really hard. But to start, we have talc. Now talc is the softest mineral and it scratches quite easily with my fingernails. So if I do that, you can see like it's effortless. It's really easy to scratch talc, and a lot of the talc powder gets on my finger when I scratch. Okay, next is gypsum. Gypsum is quite soft as well. My finger is a 2.5, fingernail is a 2.5, gypsum is a 2. So again, gypsum is quite easy to scratch. So you can see bits of the gypsum coming off, and it gets on my finger again. So that's gypsum. So once your fingernail scratches it, it's softer than and scratches it easily. It's softer than a 2.5, so it's more than likely talc or gypsum. The next thing on the list is, it's a little bit tricky to come out. It's calcite. Having some, there we go. So this is calcite. Now, calcite is kind of funny to me sometimes, because I realize, like my work in the field over the years and so on, that you can get a scratch from calcite with your fingernail. So calcite is a 3 on the Mohs scale, but your fingernails are 2.5. You can get a scratch on it, but it's kind of hard. So you have to put a lot of force into it to get a scratch, but it can happen. But with a copper coin easily scratches calcite. You see that even bits just broke off, so that's quite easy. It's easily scratchable with a copper coin, because a copper coin is a 3.5, whereas calcite is just a 3. So that was effortless. Then there is fluorite. So you have, let's go back through the list again. So there's talc, gypsum, calcite, fluorite. Fluorite is a 4. So it's a 4 on the Mohs scale of hardness. But my glass is a 5.5, so it's significantly harder than the fluoride, and it's easy to scratch with the glass. You can see there are little bits of fluoride that are coming off when you scratch it with the glass. So that's quite easy and somewhat effortless to scratch with the glass. Now, there's another mineral called orthoclase. So it's talc, gypsum, calcite, fluoride, apatite, orthoclase. And this is orthoclase. And this is a steel nail. The steel nail is a 6.5. The orthoclase is a 6. So the steel nail scratches, can make a number of scratches easily with the steel nail. So you can see makes a scratch right there on the orthoclase crystal. So anything above the 6.5, the steel nail, you have the quartz. The quartz is 7. Quartz is a bit harder to scratch with the steel nail, incredibly hard to scratch. You need something like a drill bit to scratch the quartz. And when you get all the way up to like corundum is a number 9, and moissanite and or diamond, it's a lot more tricky and challenging to scratch. It is said that only a diamond can scratch another diamond, and in this case only a diamond could scratch a moissanite. So that is it in a nutshell. So the key takeaway, talc and gypsum scratch easily with your finger, but if there are any other minerals other than talc and gypsum, you're going to likely need something like a steel plate or a nail or a coin to test it, and that's it. So it's pretty straightforward once you get the hang of it. Now, as I said earlier, color is often unreliable in diagnosing what a mineral is. But where color fails, streak gives you more confidence. Streak is simply a mineral in powdered form, and we test the mineral streak by rubbing it on a rough piece of porcelain called a streak plate. The streak or powder for many minerals is often a different color from the mineral itself, right? So an often used example is pyrite, which I have a piece of here from my personal collection. And pyrite is sometimes called fool's gold. I don't know if you remember, there was an incident some years ago in the parish of Hanover where people found pyrite like this and thought it was actual gold. So yeah, that's what happens sometimes. People might see it and think that it's gold when it's not. But gold leaves a yellow streak, whereas pyrite would leave a black streak. So I have the pyrite here, and I'm going to just take it, and there's this little piece here, and I will just rub it against the steel plate. And then you notice that black mark that's left behind. That's the mineral pyrite in powdered form. So gold would leave a yellow streak, but pyrite would leave a black streak. And it's as simple as that. Some metallic minerals, primarily those containing iron, are quite magnetic. This is due to the arrangement of metallic bonds in some iron minerals. And recall in the last episode where I mentioned ionic, covalent, and metallic bonds. Here I have mineral magnetite. And it's called magnetite for obvious reasons, because it's magnetic. And it's from my personal collection. It is one of the most common magnetic minerals. And I also have a magnet. You see the North Pole, South Pole, so I have a magnet here. And it's pretty straightforward, really. Like, you can lift bits of the magnetite with our magnet. So like that. Like that. Oh. It's kind of fun to play around with. But in Jamaica, there are a couple of beaches in which the sand is quite magnetic. For example, Farquhar's Beach in Clarendon, which is a little bit south of Milk River Mineral Bath, and then there is Alligator Pond at the border of Manchester and St. Elizabeth. And the reason the sand there is magnetic is because of the mineral magnetite. So in the structure you have titanomagnetite and titanohematite in the sand, just like these bits of rock that I have in front of me. And that's it. Quite simple, straightforward. And magnetism is good. And if a mineral is magnetic, it really narrows it down to what exactly it could be, because there are not a tremendous amount of minerals out there which show high magnetism. So if it's magnetic, it really helps to narrow things down a little bit. Okay, so double refraction is an optical property of a mineral, and it occurs when a single ray of light enters a certain mineral like Iceland spar calcite. And when the ray of light enters, it splits into two rays of light. And double refraction is called by other names like birefringence or anisotropism. But for simplicity, we will stick with the common name double refraction. So on a piece of paper like this one that has a word on it that says subscribe, when you have a word on a piece of paper like this and you put the calcite on top of it, the word appears twice. I hope this works and you're able to see it. But the word subscribe, you can see it lift off the paper sort of, and it appears twice. Yes, so as you know, viewers and subscribers, on this channel we like to try our best to keep things as simple as possible. I wanted to explain a little bit more about the double refraction that's occurring in the calcite crystal that we looked at earlier. And this is the simplest schematic diagram that I could come up with. So here you have the calcite crystal. There's an incident ray of light. So to think of this as a ray of light, it enters the calcite crystal and then it is split. Hence the word double refraction. So you have an ordinary ray, it splits going this way, and then another one split going that way. And that's why you have two images. So this is the most common test that you'll see a geologist do in the field. And I think sometimes it's even abused, because I've seen people just douse rocks in hydrochloric acid when all you needed was a few drops. But anyway, I have here a limestone, and limestone is rich in calcium carbonate, CaCO3, and I have 10% solution of hydrochloric acid. Now, what you do, you take a few drops. So let's pull the bottle here, right? And you just need a few drops on the surface of the limestone. And then you notice that there is effervescence occurring, lots of bubbling, and if you can hear a little bit of fizzling too. And that is pretty much it. So that's a diagnostic property. So if you see a rock fizz like that in the presence of hydrochloric acid, it means that it's some sort of carbonate. Okay, so as I did with the double refraction segment, I decided to take my whiteboard again to explain the reaction that you saw earlier. So this is the equation of the reaction. Over this side of the equation, you have the reactants, which are calcium carbonate, calcite, which makes up the limestone. It's a solid, plus the hydrochloric acid, which is an aqueous solution. So these two react together to give you calcium chloride as one product, which is an aqueous solution, plus water, another product, and most importantly, carbon dioxide gas. And that's what caused the bubbling that you see. So I just have it down here with the little bubbles. So that is what really is seen with the naked eye, the carbon dioxide gas escaping. And that is it. All right, so we are at cleavage now. So just so we are clear, this has nothing to do with the common use of the word cleavage to describe a woman's bosom. In geology, mineralogy, and material science, cleavage can simply be defined as the tendency of a mineral to break along planes or areas of weakness. The areas are associated with zones of weak atomic bonding within the crystal structure, and these planes or flat areas along the mineral are repeatable and as such are predictable. So some minerals are known to have a common cleavage. Muscovite, which is a type of mica, has one cleavage direction and it's kind of flat and flaky, you know. Orthoclase, a kind of feldspar, has two cleavage directions. Halite, an evaporite mineral, and calcite, a carbonate mineral, they both have three cleavage directions. Fluorite has four directions of cleavage. But fracturing is a little different. So in fracturing, if all the bonds in the mineral are equally strong, the mineral will fracture instead of cleave. As I mentioned earlier, with cleavage, there is repeatability and there's predictability along the planes which the minerals break. But with fracturing, there is irregularity or even roughness in how the minerals break, creating uneven sort of surfaces. Chert, a type of microcrystalline quartz, and obsidian, which is volcanic glass, are known to fracture in a manner known as conchoidal fracturing. And this is where the minerals break in a way that, well, they sort of shatter and they produce smooth and curved surfaces. And most books would say something like the broken pieces resemble the inside of a seashell. And though that is quite accurate, I like to think of conchoidal fracturing like bits of broken tile. If you ever watch a tiler at work in your homes, offices, or business places, after they measure the dimensions of the room, they may use something like a hatchet to kind of hack the bare concrete floor to even it out. and then they sweep away the excess dust and start to apply the thin set to lay the tile. Sometimes a tile or two breaks or shatters, and the way they fracture is similar to how conchoidal fracturing works. Sometimes these broken tiles are arranged in the floor in a pattern, and sometimes it's not intentional and they just toss it out, you know? So that's the best way I can describe conchoidal fracturing. So other diagnostic properties now. Well, there's taste, right? And so let me caution here. I am not encouraging anyone to go out there and taste any mineral. So please, in the very cliche words I often hear on television programs, please do not try this at home. Never taste a mineral, especially when you don't know what it is. Minerals, and metallic ones in particular, can be quite toxic. I think of galena, for example. That's what really comes to mind. Anyway, I share taste because a common example in which a geologist will lick a mineral is to find out if the mineral in question is halite. Halite is sodium chloride, just like the salt in your cupboard at home. The difference is it forms in large cubes in environments with high evaporation. So think dry semi-arid regions, and a saline body of water like a lake or a pond. But my point is that sometimes cubes of halite can look almost like calcite, and geologists can, or they may, lick the surfaces of the mineral to see if it's salty. But I may have been guilty of this in the past, but I would never encourage anyone to do this. So piezoelectricity is another one, and it's the ability of a mineral to generate an electric charge when mechanical pressure is applied. And a common example of this is the mineral quartz. And this property is quite useful industrially. So have you ever looked at the faces of those traditional ticking watches and seen the word quartz on the face? This is not a brand name. What that means is that your nice, clean, vintage Bashment watch has a quartz crystal in it. Now, I'm not a watchmaker or a jeweler, but I believe the process works via a tiny quartz crystal which vibrates when powered by the watch battery, and it helps to keep accurate time as quartz vibrates at a known constant frequency. Other minerals known to possess this property are tourmaline and topaz. Then we have fluorescence, right? Some minerals glow when exposed to ultraviolet light, but under the right conditions, of course, like if impurities are in the mineral structure. Some common fluorescent minerals are aragonite, pyrite, chalcedony, fluorite, and even calcite. But remember, these minerals may not glow in all cases when exposed to UV light, as the right type of impurities have to be present. And then there are also laboratory methods. And outside of the initial diagnostic tests, which I showed you much earlier, you can take your minerals to a lab and you can run tests like XRD, XRF, and ICP-OS. I will talk about these things in future episodes. So why does this matter to us? Well, knowing the properties of minerals is essential in knowing how they behave in things like our electronics and in maintaining the structural integrity of our buildings. Knowing how to identify them can help us know what is of significant economic importance and what isn't as economically significant. Minerals are important in our everyday lives. I mean, I am recording this video on a device, uh, and it has a lot of electronic parts. And you are probably watching me from a smartphone or laptop or tablet or smart TV, and all these devices have mineralogical components in their circuitry. So in a way, you can say that minerals make it possible for us to interact with each other via this YouTube platform. And I can go on and on, from medical devices to the house you live in made from cement and steel, to your favorite cars, to planes in the air, to toothpaste, to makeup, to medications, and more. Minerals are key in all of them. So, to sum everything up, a mineral is a naturally occurring inorganic solid substance with a defined chemical composition and crystal structure. There are several ways to identify a mineral, including color, which may at times be unreliable, but there's also streak, there's hardness, interaction with acid, optical properties like double refraction, and more. And they are important to pretty much all aspects of modern human living. So that's it for this episode, but I hope you enjoyed it. And in our next episode, we continue with minerals, but this time we are going to look at how they are classified. It should be interesting. So look out for that. Stay curious, and comment and let me know what you found interesting about this video. So take care, and I'll see you next time.